Okay. Having breakfast. First it's breakfast. Did this computer turn off? I don't recall turning that computer off. I have zero recollection of turning this one off. Is this like, did this lose juice or something? Computer crisis. Is this not plugged in? Would you declare? I don't think this is plugged in. Computer won't turn on. Oh man, my. Alright. Let's plug this somewhere else and see if that's not plugged in. Oh wait, so now it is turning on. Hang on. Turns out the computer is turning on. It's just really slow. Okay. So, this is my breakfast. I'm having raisin bran and okay, there's my phone. Oh no! I started streaming before I organized my room. That means I don't know where anything is. It's fine. Okay. However, I don't see myself. So that's not good. I'm going to turn the resolution down on the camera because I don't see myself. And we'll start streaming again. I switched the output to 864. This is what it's like trying to stream on a MacBook Pro. It doesn't really work very well. But whatever. Let's see if this computer can see it. What? I don't want to fucking see his ugly face. Okay. Let's eat this. Eat some brekkie. I don't have to eat much. Okay, now let's turn on the speaker, listen to my book. Just remembered that right now. Okay. Settings, Bluetooth, Logitech adapter. I have to completely disconnect the Logitech after every time I use it, or else it connects automatically all the time. Alright, so now for the book. Quantum physics.
Is more similar to
Here we are.
the V direction than it is to the H direction. This idea of similar to into a probability, which is a
Alright.
number. According to quantum theory, you can do
Quantum
this
dynamics.
just by making drawings
Oh look, I can.
and
Alright.
analyzing the geometry.
Let's see if I can
Imagine
see
such a
myself on this
case
computer.
for
I'm just
dipole
super
photon.
curious.
On the left is a
Let's see what we
rear-end
got.
view of the light beam
Ooh.
traveling away from you, and the tilted line
Disconnected to the internet.
represents the polarization.
Oh
The
no,
photon's
my
polarization
freaking
direction
video
is
is
Calcite
sideways.
crystal used to analyze
God,
this
I hate it when
photon
that happens.
has a unique axis, which is oriented
My
in the
vlog
V
from this
direction.
morning is sideways
In
again.
this case, the polarization
Still haven't
is
figured out how it gets
similar
like
to
that.
the H and V direction.
Alright, so here
we
I am.
expect the probabilities of these outcomes to be equal. We also know the two probabilities must add
Alright.
up to 1, so each probability must equal
Good business.
0.5. Imagine there is a triangle
plug
with the
in.
two short sides in the V and
Plug
H
in. Oh, I can't.
and the long side in the direction of the
God, I want my
photon's
cable.
polarization. The
Sorry if
length
there's
of the
bad
polarization
sound, but I haven't
equals
gotten my
1.
extension cable for my
Reflect
mic
the
yet.
probabilities must add to 1.
Alright.
The short lines are the components of polarization along the directions V and H. Their lengths are indicated using the letters A and B. Notice that the three lines form a right triangle. We know from the Pythagorean theorem that for a right triangle, the sum of the squares of the two short sides equals the square of the long side. Because 1 squared equals 1, we have the relation A squared plus B squared equals 1. Here we make a conjecture, which was first made by physicist Max Born in 1925. The idea is that we want to arrive at a formula containing two probabilities that add to 1. For this reason, Max Born identified A squared as the probability for the photon to exit in the V-pole beam, and B squared as the probability for the photon to exit in the H-pole beam. This identification is called Born's rule. It has been found to be in perfect agreement with every experiment ever done concerning the polarization properties of photons. Born's rule is easy to apply simply by drawing figures and using a ruler. Redraw the triangle shown on a sheet of paper such that the length of the polarization line is 1 meter. Let's refer to this length as 1, without including the word meter. Then, if you use your ruler to measure the lengths of the other two sides, you will find lengths A and B both close to 0.707. If you square this number, you will find 0.707 squared equals 0.5. So, according to Born's rule, the probability
frozen.
to observe detection events in the V and H beams both equal 0.5.
Whatever, dude.
This is in accordance
What's my
with our
phone look
earlier
like?
expectation that the odds are 50-50 the
This
photon
is as good
will
as I
take
can
either.
go on it.
So Born's
I'm at
method
8.
works in this case.
800
Consider another
resolution.
example. Let's say
1000 bit rate, which is what YouTube recommended.
Protagonist named Alice.
So if this is all we
Let's say
got,
the
this is all we
polarization
got.
direct-
Bit rate, which is what YouTube recommended. Oh wait, looks like we're good. I'm just paranoid. That's what my problem is. Fucking paranoid. Okay, how do I get my book back?
30-degree angle with the H direction. Alice verifies the polarization angle by passing the photon through a calcite crystal oriented at 30 degrees from H. The photon passes the test. Now she sends the
Alright.
photon to another protagonist named
My breakfast
Bob, who does
consists
not know
of
the photon's polarization. We encountered
Raisin bran.
Alice and Bob many times in this
one
book,
bowl of
so
raisin
let's
bran.
get acquainted with them. To measure this photon, Bob chooses to use a calcite crystal in the HV orientation. How do we predict the probability the photon will
What is
exit
this
this
bulb?
crystal in the H-pole beam? Perhaps you can determine intuitively which measurement outcome will have the higher probability. Which polarization, V or H, is the photon's polarization most similar to? If you thought H, you were correct. The polarization is tilted more toward H than toward V. How can we use Born's rule to determine the value of the probability? Imagine a right-angled triangle made up of lengths A, B, and 1. If you use a ruler to measure length B carefully, you find a value close to 0.866 in this example. The probability for the H-pole outcome is then 0.866 squared equals 0.75. That is a 75% chance the photon takes the H-pole beam path. If you use a ruler to measure length A carefully, you find a value close to 0.50. The probability for the V-pole outcome, that is perpendicular to the H-pole, would therefore be 0.50 squared equals 0.25. That is a 25% chance the photon takes the V-pole beam path. All is well, since 0.75 plus 0.25 equals 1.0, as it must be. We will hear in later chapters that the Born rule applies to many situations in the quantum realm.
Alright.
If you follow the reasoning in this section, you are now an expert in an
Go to the
important part of
restroom
quantum theory.
and then we're hitting
If
it.
not, no worries. Let's move onward. What does it mean to make a measurement in the quantum realm? To summarize the previous discussion, all experiments on measuring photon polarization involve three parts. 1. The preparation of a photon. 2. The choice of calcite crystal orientation. And 3. The occurrence of a particular measurement outcome at a detector. A few important comments about these steps. There are infinitely many options for the choice of calcite crystal orientation to be used to analyze a photon's polarization, and for a given measurement you can choose only one of them. I will call the chosen crystal orientation the measurement scheme. For a given measurement scheme, there are only two possible outcomes, the probabilities of which add to 1. There always exists one choice of measurement scheme, for which the outcome can be predicted with 100% certainty. That is, when using this special scheme, one of the outcome probabilities equals 1, whereas the other equals 0. So what does it mean to make a measurement in the quantum realm? Many deep-thinking physicists have tried answering this question. To quote one, Sir James Jeans, in 1943 wrote, "Our minds can never step out of their prison houses to investigate the real nature of things, gold, water, centimeters, or wavelengths, which inhabit that mysterious world out beyond our sense organs. We are acquainted with such things only through the messages we receive from them through the windows of our senses, and these tell us nothing about the essential nature of their origin." Jeans is getting at the fact that any measurements made on a single photon cannot determine its polarization, yet a particular measurement does yield some definite outcome. The measurement outcome does not correspond directly to a past definite property of the photon. From such a measurement, we can receive only a limited amount of information about the photon's polarization. Again, if we detect the photon in the V outcome detector of an HV calcite crystal, the only thing we can say with certainty is that the photon's polarization was not H. As Jeans says, it is as if the photon is sending us a message that contains some, but not complete, information about the question we ask. What is measurement complementarity? The outcomes that are possible from an observation of a photon's polarization depends on how you choose to set up your experimental apparatus. That is, your measurement scheme. For example, you can set up your calcite crystal to find out whether a photon yields the outcome V-pole or
Let's get
H-pole.
some
Or you can set up your crystal to find out whether a photon yields the outcome A pole or D pole. But
Back the
with
window
a
just a
photon,
little
you
bit.
cannot do both.
All
You
right.
can't turn back the clock and proceed as if you hadn't made the first measurement. You might think, well, I can make a sequence of measurements. First measure using the HV scheme, then measure using the DA scheme. And the trouble with this proposal is that the first measurement actually changes the polarization of the photon in an uncontrollable way, which defeats your goal. Imagine such a setup. There's a detector labeled V detector in the D-pole path. If that detector does not register an event, then you know the photon took the H-pole path. When it reaches the DA-oriented crystal, according to Born's rule, it then has a 50-50 chance to be registered at either the A-pole or D-pole detectors. But this 50-50 chance has nothing to do with the original polarization of the photon, because that was changed during the HV measurement.
Okay.
Niels Bohr, a highly influential
I need
Danish
my-
physicist in the 1920s, introduced the concept
I
of
need my,
measurement
yoga mat.
complementarity to describe the fact that for a given photon,
know that
you
there's
can't do
someone
both
around here
measurements
very
HV
close.
and DA independently. He said that the V or H pole observation is complementary to the D or A pole observation. Bohr's idea of measurement complementarity applies not only to photon polarization orientations, but also applies, for example, to the position and velocity of an electron.
Okay.
They cannot both be observed independently for a single electron.
Okay, so
How can a human
need my
scale
Apple
object seem to
Watch.
possess definite properties if the individual
There it is.
quantum objects making it up do not?
so
Well,
far
we can't
successful
determine
finding
the
things.
polarization orientation of
Oops,
an
we
individual
were missing
photon.
two lights though.
But if the beam is
Three
composed
lights.
of a very large number of
Just a sec.
photons, each with a possibly different polarization orientation, we can determine the average polarization
One
orientation
light.
of the beam. We can do this by rotating slowly a calcite crystal that is placed in the beam.
Ow, hit my
And
head.
for each angle, recording the fraction of photons that exit neither beam from the crystal. Let's say we find a crystal orientation for which the maximum fraction of photons is detected in the lower beam exiting
Now
the
you have
crystal.
all the lights.
This particular crystal orientation
So
is the
good.
average polarization of the beam.
I'm gonna move this
Consider the
computer
light
up here
beam
so that I can control. I should connect it to the other.
You can say we have
keyboard.
determined its
Let's do that.
polarization. Although individual quantum objects don't possess
There it is.
clearly describable properties, when
I'm
a
not
large
totally
collection
sure
of
it's
quantum
even.
objects come together to create something that we humans perceive as a human scale object,
I'm not sure
then our
if this
human
is
intuition allows us
charged. Oh look, a phone call. Hola. Está bien. Ajá. Estoy streameando ahora. Puedes verme en YouTube. Oh my god, streameando. Stream. Look, it's my. Sí, on YouTube. In YouTube. Okay.
Para poder cuando tenga tiempo te pongo ahí en tu oficina, mientras yo cocino, hago cosas, te puedo ver, ¿me entiendes?
Sí.
Porque esta semana estaba con la Lucy y hemos hecho como estas cosas. Aparte que
It's not charged.
se llama, ella
Battery's dead.
consume, me absorbe mucho.
Uh-huh.
Absorbe la Lucy. Es tipo, después ya tiene tiempo de hacer muchas cosas, como salir de la casa, y esto de ir a buscar audio 4 veces al día,
Uh-huh.
también me quita mucho tiempo, ¿me entiendes?
Uh-huh.
Y nada, bueno, voy a usar la temperatura, la temperatura de la velocidad. Y hay una cosa que quería decirte, pero no te preocupes, papá de la Lucy positivo
Oh.
para el COVID.
No, no. ¿Está en el hospital?
No, que lo traen a la casa. Oh, se ve que no grave, o sea, no tiene síntomas como... Porque yo hablé con él y me dijo que no tenía fiebre, que era solo tos, resfriado.
Bueno, Paula, cuidado a ti porque tú fumas y tú no quieres tenerlo. De Lucy.
Sí. El problema es de que la luz tuvo contacto con él, ¿me entiendes?
Ajá.
Y prácticamente la luz la mandó al tiro a la pediatra a hacer el tampón.
Ajá.
Así que me van a llamar mañana pasado para hacer el tampón y también pedí para mí Claudio.
Ajá.
Así que me van a llamar a todos para hacernos el test, ¿me entiendes?
Ajá.
Todo por culpa de este hijo de puta que no se cuida y anda en giro, anda dando vueltas con los amigos, ¿me entiendes? En los bares.
Sí.
Porque no está quieto, o sea, no está...
Responsable.
no es responsable, ¿me entiendes? Entonces, el cosa es que sí, esperemos Dios quiera que no, la luz esté bien, pero la luz está con síntomas, está con tos,
Oh, no.
está tos.
Tú vas a tener que tener máscara con ella. ¿Alrededor de la casa o no?
Yo en la casa de estos días, yo supe ayer en la noche que se iba a hacer tampón con la Lucy, porque ni siquiera me lo dijo a mí. Y después, hoy día, me llamó él y me dijo que había salido positivo.
Oh, no.
Tampón. Yo ahí me preocupé, obviamente por la niña, ¿me entiendes? Me
Sí.
preocupaba por ella y porque ella tiene tos, como ya está en dieta, está con tos,
Ajá.
pero yo pensé que era un resfriado, basta.
Ajá.
Pienso que es un resfriado, tratando de pensar positivo, quizás solamente un resfriado, que Dios nos ayude y que no sea nada más, ¿me entiendes? Porque la luz, como te digo, es mala para comer, es mañosa. Toma tantas como vitaminas, con vitaminas, ¿me entiendes?
Ajá.
Ay, no sé. Estoy un poquito ansiosa, pero pido tanto a Dios que nos ayude y que todo salga bien y
Espero que él no la da a su madre, porque la madre tiene como 80.
la mamá de él tiene, sí, 26 años más o menos.
¿Ella tiene vacuna?
No, todavía no me han vacunado,
Hmm.
pero la mamá me dijo que le iban a ir a vacunar a la casa.
Ajá.
Yo pienso irme a ir mañana
Ajá.
a vacunarla y yo lo que le pedí yo además es ir a vacunar a la casa
Ujú.
porque es muy anciana, conozco muy anciano y el otro que no tiene, él no puede salir de la casa y no tiene nadie que la lleve, o sea, no hay nadie que llevarla porque tiene miedo obviamente de puede infectar, ¿me entiendes?
Ajá.
No se sabe porque puede ser que la mamá de ella no lo haya cogido, ¿me entiendes? Que no lo tenga, la mamá
Ujú.
de ella.
Ujú.
Y yo espero que la Lucy él lo haya cogido después, ¿me entiendes? Lo
Ajá.
haya tomado después, porque la Lucy se vino conmigo el domingo, se vino a la casa
Ajá.
y empezó como 3 días con esta tos, más o menos.
Oh, no. Pucha.
Sí, amor. Este maldito COVID
Sí.
está volviendo loco al mundo, está cambiando el mundo completamente.
Mhm.
Es el caso más cercano que he tenido, digamos, más cerca que esto. Pero, bueno, tú me contaste que tu mamá era positiva o ella pensó que era positiva.
Está vacunada. Ella en el principio creyó que contractó, pero tuvo examen que fue negativo, pero ella no lo cree, cree que tuvo igual. Yo no creo que tuvo.
No lo tuvo, no, imposible. Si el examen salió negativo, significa que ella no lo tuvo. ¿Entiendes?
Ajá.
Si ella está vacunada, tiene que estar más tranquila, ¿me entiendes? ¿Cuánta vacuna para poner allá?
Es gratis.
Sí, acá también es gratis, pero ¿cuántas van a poner?
Dos.
¿Una o dos?
Dos.
Igual que en Chile.
Pero creo que hay uno nuevo que es solo uno.
Mi mami le pusieron una ya a mi mamá y le van a poner digamos, la segunda que la tienen que llamar.
Mhm.
Así que tienen que esperar la segunda vacuna.
Ajá.
Pero es de esperar que nos llegue a nosotros, digamos, a las personas de mi edad, a la Lucy. Además, que será mucho que en Italia, yo no sé cuánto tiempo.
Mhm.
Porque todavía están vacunando a las personas acá que tienen 80 años, ¿verdad? O sea, los 80, los 90, están 200 todavía acá.
Mhm.
No han llegado todavía ni siquiera a los 70.
Mhm.
Entonces está muy lento aquí en Italia.
Mhm.
Ese es el problema.
Aquí también.
¿También está lento allá?
Sí. No hemos llegado a 70 tampoco.
¿Cómo tu mamá se la puso particular?
Tiene 79.
O sea que ya de los 80, 90, 80, no sé, lo pusieron.
Sí.
Acá están de los 100 años, empezaron.
Ajá.
100 años, 90, 90, 80, están ahora parece.
Ajá.
Igual están atrasados. Y dijeron que iban a llegar 40.000 millones de vacunas. Iban a llegar.
Mhm.
Y de ahí tendrían que estar vacunados más o menos casi todo el país. Pero todavía faltarían vacunas.
Ajá.
Porque en Italia son 60.000 millones de habitantes.
Mhm.
¿Entiendes?
Entiendo.
Estados Unidos, ¿un cuánto?
350 millones.
¡Wow! Son 1, 2, 3, 4, como 5 veces más que Italia.
Sí.
Oh, mamma mía. Oh, amor mío, amor mío. Y esta va a tener que poner particular. Porque cuando lleguen a tu edad, va a pasar mucho tiempo.
Mhm.
¿No pensaba uno en ponerse la particular?
Mhm.
¿Tú que tienes el problema de asma?
Sí, yo no quiero contratarlo.
No quiero contraerla, sí, es contraerla.
Contraer.
Contraerla. Pero si no quieres contraerla, tu mamá tiene que hacer algo porque tú eres asmático.
Sí.
Para que te la pongan antes, ¿no entiendes?
Sí. No, estoy en mi casa. Yo nunca voy a contraerlo. Estoy en mi pieza siempre.
Pero, por ejemplo, tu amigo, tú no sabes con quién es tu amigo.
Sí, pero él está solo también siempre. No tiene amigos o trabajo. Solo está solo, caminando por la calle.
Y cuando trabaja, no habla con la gente en el trabajo.
No trabaja, no tiene trabajo.
Ah, no trabaja.
Sí.
Oh, qué vida más aburrida que tiene.
Sí, está en la casa siempre. Y dentro, afuera, dentro, afuera.
Oh, mamá. Mire, mi amor. Y los papás le pagan el arriendo, le
Sí,
pagan todo, ¿no?
exacto.
Papá.
Sí,
No le da vergüenza.
sí. Pero él no quiere trabajar.
No quiere trabajar.
No puede.
Ah, no puede.
No, no, sí, no. Nadie lo contrata.
¿Y por qué? Porque tiene muy mala decencia.
Sí,
O
mala atención al trabajo.
tiene un carácter muy malo.
Sí.
Pues sí, un carácter malo. Comúnmente va a ser difícil que lo contraten, ¿me entiendes?
Sí.
¿Cómo te soporta, mi amor? My love, my darling. Un hombre con un carácter así en la casa de tu casa.
Yo estoy en mi pieza siempre.
Pero en tu casa tú puedes hacer lo que quieras.
Me deja usar el auto.
Menos mal.
Y no lleva amigos aquí que me gusta. Me gusta tener mi paz.
Eso es bueno. Ni mujeres.
Sí, ninguna mujer. Solo la vecina viene.
¿Qué vecina?
Una vieja quien siempre quiere ayuda.
¿Cómo? ¿Los ayuda a ustedes o piden
Mi compañero de casa la ayuda.
Porque ya anciana, ayuda con el peso.
Cosas
esas
así,
cosas.
sí.
O en la casa, luz.
Sí, llevando cosas.
Pero eso es amable.
Yo la ayudo una vez.
Bueno, pero tú tienes tu madre, hay que preocuparte,
Sí,
¿entiendes?
sí,
Tú tienes a quien ayudar, a quien cuidar,
sí.
porque... bueno, amor, bueno, tú cuídate mucho y basta. Lo importante es que ya la loca no va más para allá, que la loca seguramente ya tiene contacto con más gente, porque ella tiene que ir a la escuela, tiene que hacer cosas, moverse un poco, tiene más contacto, que tiene gente viviendo en
No,
su
ella ya
casa.
lo contrató.
Lo contrajo.
Lo contrajo. En el principio.
Y, ¿de verdad? ¿Seguro? ¿Y te mostró los
Y
papeles?
no
¿Lo viste?
junté con ella de nuevo.
Y después no la viste más.
Sí, no estoy hablando con ella.
¡Wow! 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 Eso sí que me encanta. Ese es mi Kyle. ¿Cómo se dice? Ese es mi Kyle.
That's my Kyle.
Es más, es o is. My
That.
Kyle. That's my Kyle.
Mhm.
That's my Kyle. Oh my God. He's a miracle. It's a
Mhm.
miracle. De
Me
verdad
dijo
es un
que
milagro
iba a
que no-
llamarme en el principio de marzo. A ver.
¿Cómo?
Me dijo que iba a llamarme en un mes. En el principio de marzo.
Oh my God.
Pero no sé si
Oh
va a
my-
hacerlo.
Oh my God, es terrible esa mujer.
Sí.
Ella, tú aceptas todas las condiciones que ella te pone. O sea, no sé, tú eres tan débil con ella, yo no sé por qué.
Estoy viviendo diferente vida ahora. Estoy ejerciciando siempre ahora. Empezando con ayer. Hoy es mi segundo día.
Wow, así me gusta. Va a ver, mira, yo también estoy sola.
Estoy
También
estirando
sola,
ahora.
vea. Está súper, ¿me entiendes? Yo igual estoy sola, pero yo te dije que quería hacer ese curso para poder trabajar y me dijeron que todavía no podían como inscribirme porque le falta gente.
¿Qué curso?
Es un curso se llama, tengo que mandártelo, es como masaje para kinesiología,
ok.
como principiante, digamos, de kinesiología.
Ajá.
Porque para ser kinesiólogo tienes que ir a la universidad 3 años
Oh, qué bueno.
para poder ser un kinesiólogo. Tú podrías hacerlo. Tú puedes.
No, yo tengo mi propio carrera.
Sí, yo sé, mi amor. No, yo te digo, porque tú eres bueno para los masajes. Sería un excelente kinesiólogo.
Sí.
Serías muy bueno y tendrías, no sé, esa clientela. No sé, yo voy a probar. Voy a probar porque quiero hacer algo en mi vida, ¿me entiendes? Con mi vida.
Tienes que ser fuerte. Tienes que ejercitar y levantar peso si quieres ser una buena masajista.
Eso voy a hacer pesas.
Pero puedes ganar dinero y puedes trabajar solo. Puedes viajar y todo eso. Es un buen trabajo si lo haces correcto.
Sí, sé. Lo otro también que puedo trabajar en spa o en partes donde hacen masajes.
O solo. Puedes ir a la casa de gente.
Sí, también. Por ejemplo, o como tu hermano, ¿me entiendes?
Sí.
Como Windows, cosas así.
Exacto.
Solo lo bueno es que me gusta, o sea, después la fuerza, esperemos de, obviamente no voy a tener la misma fuerza de un hombre, porque los hombres son más fuertes para eso.
Ajá.
Pero yo espero que de verdad poder tener es que no sé, tengo que el tipo con el que yo hablo, que está por WhatsApp, él es como súper estúpido para responderme. Mira, esta cocina de acá no puedo. Yo estoy como diciéndole, ¿cuándo puedo pagar el dinero para por la inscripción? Y él está como, oh, tienes que esperar porque falta gente, no sabemos, oh. Y yo estoy como, pero mándame una respuesta cuando tengas algo seguro.
Ajá.
Ok. No, ni siquiera me respondió el último mensaje.
¿Quién?
El de la escuela de masaje.
No.
Ah,
Tal vez puedes ir al otro o estudiar solo con tus hijos y empezar chico.
hay uno que lo dan por online. Igual me título, ¿me entiendes? Con el computador, por online, que digamos con el colgante y todo, bastante. Pero este cuesta mucho menos. Pero te tiene una persona para practicar. Y Claudia tiene horarios medio extraños. La Luz no está todas las semanas conmigo, así que ver quién puede ese día ayudarme a practicar para los masajes.
Ajá.
Porque si Claudia está trabajando y si la Luz está con su papá, no tengo a nadie con quien practicar.
Yeah.
Tengo solo mi
Tal vez hay otras escuelas. Tal vez hay en otra escuela.
La única esta que yo vi, que el tipo es súper tonto para responder, esa de ahí, digamos, es bueno porque yo te conté que la hacía en un hotel que está al frente de mi casa.
Ujú.
Y ahí tú lo haces de persona. Digamos, está todo el curso, está toda la gente.
Ujú.
Es como lo que yo veo es la manera más fácil y más rápida de aprender.
Ujú.
Porque ahí tú sabes, te enseñan y te dan el título, te dan todo, prácticamente son 2 días, 2 o 3 días. ¿Entiendes? Para aprender.
Ujú.
Es poco.
Ujú.
3 días, pero bueno, en 3 días yo tengo ya un título.
Ajá.
Después puedo sacar otro, después otro. Y así de a poco ir sacando más y más y más títulos para poder, no sé, hacer todo lo más que pueda. Y los que vea que hay que hacer mucha fuerza, eso trato de no hacerlo.
Ujú. Sí.
Porque hay unos que son, ¿te acuerdas los que hacías tú? De estirar,
Ajá.
para estirar. Para eso tienes que tener fuerza, mucha fuerza.
Ujú.
Es más fácil, yo creo, para los hombres, estirar los músculos.
Ujú.
No sé, te lo voy a mandar y tú me puedes más o menos decir si está bien para mí o no, hacer ese curso.
Ujú.
Yo tengo que hacer cosas con con las manos y no usar tanto la fuerza.
Ujú.
Así que bueno, ahí voy a ver. Tengo que esperar que se llene el curso. Así que... Y cuéntame, ¿qué estás haciendo más aparte de eso?
Solo esto. En mi sitio web estaba haciendo cosas locales aquí. Estaba dibujando todos los caminos en las montañas para que pueda tapar civilización aquí, para que en el Google Earth la única cosa que ves es naturaleza como 1000 años atrás y con los caminos encima para los bicicletistas aquí. No está conectado a mi sitio todavía. Voy a hacer eso hoy. Estoy estirando todo el día hoy y estoy muy mal forma. Este es mi primer día ejerciciando.
Ah, ok, constante.
Sí.
Yo me gustaría mucho hacer esa cosa contigo, por ejemplo.
Ajá.
Hacernos juntos,
Ujú.
pero o por Skype, porque yo tengo Skype en un computador de caca que me compré, porque es un computador súper complicado. No sé.
Todavía te enviaré mío cuando tengo dinero. Estaba gastando mucho últimamente. Tengo 4 cámaras grabándome, 5 cámaras, 4 externales. Y toda mi pieza es verde. Deberías verlo, es lindo.
Si manda un video, puedo verla.
Ok, ahora te mandaré mi canal. A ver.
Mándame a canal, así lo veo. Ahora yo estoy aquí en tu página, está viendo todas las cosas que te han mandado. Te han mandado tantas cosas. Increíble, como esta foto por el fondo, a ver si me gusta.
Sí, es chiquitita todavía. Muy niña. Okay.
Dice Carl Holmes Strawberry.
Eso.
Lo que tú me mandaste.
Exacto.
Y si yo, por ejemplo, voy a Google, tengo que ir para ponerlo.
No, no. YouTube.
Ah, YouTube. A ver, en YouTube, porque tu teléfono. Mi perdón.
Oh, God.
Tenemos que estar en YouTube.
Oh, God.
Ajá.
Estoy estirando ahora. Oh,
Ah,
oh.
Carl Holmes. Ah, sí. Aquí lo veo.
Ya soy yo ahora, hablando contigo.
Verde. Verde como. Espérate, a ver. ¡Ay! Se siente mi voz. Se siente mi voz.
Sí.
Oh my God. Estoy sintiendo en directo. Oh my God.
¿Te escucho? ¿Te entiendes lo que estás hablando?
Ajá. Espérate, digo, me están llamando, pero Claudio me está llamando. Claudio me está llamando.
Okay. My right knee hurts. My right knee hurts really bad. I don't know what happened. I slipped on it wrong or something. Oh. 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 Mm.
¿Salido, no?
Te escucho.
Oh, okay. Yeah. This is Claudia. Sí, jodida. 10 euros. Sí, déjame ver. Pásame la bolsa. Lo pasé en la señora esa que nos llamamos siempre. Ok, tiro la bolsa. Bueno, esto lo tengo que sacar. ¿Estás ahí?
Estoy aquí. ¿Vas a ir? Estás en el auto ahora.
Sí, Claudio, ya.
Hola, Claudio. Estoy estirando ahora.
Ahora tenemos que ir. Nos vamos. Tenemos que ir a la casa de Italia.
Qué lindo.
Duty for Italy.
Mhm. Qué linda. Cuídate con el coronavirus.
Okay, baby. Love you.
Love you. Ciao, ciao.
Bye-bye.
Bye. That's
Assign definite values to properties we ascribe to that object. We perceive that a stone thrown in the air has definite values of position.
Hi.
Oh, hey, it's me. Hey, I'm thinking about ditching my mattress. I think it's too big.
Well, I haven't had time to actively problem solve that. I could relate to it tomorrow. I'm thinking a 4-inch foam mat, a 4-inch foam mattress.
Uh huh.
Kyle, go online.
Wait, isn't that what the memory foam is?
Well, memory foam, that's just a topper. That's what they call a topper.
Oh.
You put it on top of a mattress, but once you're on it, it caves in. That's not going to give you good comfort support. But Kyle, do a Google search with a couple of different mattresses, like Mattress Firm or Denver Mattress even, or even Target or Walmart.
Okay.
And see if they don't have a twin foam mattress.
Okay.
Pad. It'll be a pad, like at least 4 inches. You can't do with less than 4 inches and firm.
Okay.
And that will be lightweight to move around during the day and so on.
Okay.
My friend Karen's here for only a day, and we're going to run out and do some errands and watch a movie tonight. We're going to watch Nomadland. Do you want to see that movie?
What's it about?
It's a rental. It's Frances McDormand it's about a woman who kind of hobos through the country and meets different people and has a wide array of experiences, and she's kind of down home, and the script is supposed to be good, the editing and the scenery and the music, and it's gotten multiple Academy nods. And for her performance, especially as Best Actress, I think you'd like it. It's kind of a original person who's doing her original thing for whatever reason, we don't know, but doing a vagabond tour of the country. I think you'd like it.
No thanks.
Okay.
Yeah, I'm just gonna stretch all day.
You're gonna what? Stretch?
Yeah. And
Well,
exercise.
don't overdo it. Pull a muscle. So just, do middle of the road because you're just getting back.
Right.
Okay, you pull a muscle and then you're out for 3 weeks.
Okay.
Okay, and let's go out tomorrow and go looking.
Okay, thank you. Yeah, let's do that.
Yeah, but do a Google search
Okay.
and see what shows up.
Okay.
I know they carry them because that's what we used to use years ago.
Oh, okay, cool.
Okay.
Alrighty then.
All right.
I know what you're talking about.
Say it again.
I know what you're talking about. We used to have one.
Right. Right. Yeah. Okay.
Alright, talk to you later.
Ciao.
Bye.
And velocity at any instant of time. The fact that a stone follows a definite trajectory is common sense, and there is no reason to doubt it. Yet the stone is made up of a very large number of quantum objects, electrons, protons, neutrons, for which the measurements of position and velocity would individually yield fundamentally random outcomes, just as the polarization does for an individual photon. So what do we really mean by the concept of the position of the stone? We mean the average position of the large collection of objects making up the stone. This average value has very little randomness associated with it, because the randomness of its individual constituents averages out. And this idea might help you understand what I meant earlier when I referred to classical and quantum realms. And this, of course, does not mean there are two different kinds of universes that coexist. There is only one world and we live in it. By classical realm, I mean those aspects of the world you can touch or see with your own human perception, and the properties of which can be measured without changing them significantly. We then perceive that they obey the laws of classical physics. By quantum realm, I mean those aspects that can be perceived only indirectly because they correspond to elementary quantum objects. Measuring them changes them. The classical realm appears to emerge from the quantum realm when we focus our attention on a particular human-scale object or quantity that can be touched or seen using human senses. What do we mean by the state of an object? The word state connotes condition, such as when we refer to a person's state of mind. In physics, if we know the state of an object, then we know everything possible to know about that object. What is a state in classical physics, which itself is an idealized description of nature that applies to human-scale objects? In classical physics, we can know and specify precisely the position and velocity of an object, such as a stone. There might be other aspects or properties to specify, such as rotation rate, is a baseball spinning, the full specification of classical states of an object. In classical physics, if we don't know the state of an object, we can determine it by making careful measurements of its position, velocity, rotation rate, and so forth. In classical physics, the state of an object determines precisely and uniquely the outcome of any measurement you could make on the object. So, in classical physics, the state corresponds directly to the collection of all possible measurement outcomes, all of which can be predicted with certainty if the state is known. What is a quantum state? What is the meaning of state when referring to quantum objects? Again, if we know the state, then we know everything possible to know about that object. But there are limits to how much we can know about quantum objects. Cannot know with certainty what will be the outcome of every measurement we can make on the object because in most situations these outcomes are fundamentally random. Quantum theory, however, does allow us to predict the probabilities for each possible outcome for any measurement you might choose to make on the object. So we say that quantum state corresponds to the collection of probabilities for outcomes for all possible measurements you can make on the object. In contrast to classical physics, where the state corresponds directly to the actual measurement outcomes, which are certain if you know the state, in quantum physics the state corresponds to the probabilities for outcomes, which typically are not certain, even if you know the state. In our discussion of photons, I pointed out that you can prepare the polarization orientation of a single photon, and so it can be known before any measurements are made. This known polarization orientation of the single photon is an example of the quantum state. It does not represent any pre-existing inherent property of the photon, such as position and velocity represent for a stone. Nevertheless, it represents everything that is possible to know about this particular photon's polarization, and this knowledge is independent of the experimental scheme we might adopt for making measurements. In our earlier example, Alice prepared the photon, so she knew its quantum state. But when she passed the photon to Bob, there was no way he could make measurements on this single photon to determine its quantum state. The impossibility of determining the state of a single quantum object illustrates another big difference between classical physics and quantum physics. It may seem to be a bother conceptually, but it is a boon practically because we can use this feature to build perfectly secure communication systems, as discussed in Chapter 3. Earlier, we represented the state of a single photon by drawing a line in a certain direction. We saw that by using Born's rule, we can predict the probabilities of any outcome for a particular experimental measurement scheme. Here, then, is a useful definition of a quantum state. A quantum state is a representation of everything possible to know about a particular quantum object, permitting one to calculate probabilities for fundamentally random observation outcomes in any chosen measurement scheme. In other words, a quantum state refers to as complete a description as can be given about a quantum entity or object. If we know fully the quantum state of an entity, such as an electron or photon, there really is no more information to be had. In the case of a single photon, we refer to the polarization orientation as the quantum state of polarization, whereas in the case of a strong light beam, which can be described using classical physics theory, we instead refer directly to the polarization of the light as a property of the light. This subtle difference in thinking is needed because of our inability to determine...
I should drink a lot of water while I'm doing this.
For a single photon, you can have only one try at a polarization measurement, giving only a small amount of information. In contrast, a strong light beam can be measured repeatedly, giving more and more information about its polarization state. Thus, the idea of measurement in the classical realm is an idealization that is valid for human-scale objects. For such objects, it is intuitive to believe in the possibilities of unlimited measurement precision, measurement without disturbance, and the pre-existence of measurement outcomes before any measurement is made. These concepts are behind the concept of classical state. Can Bob determine a quantum state experimentally that was prepared by Alice? Although Bob cannot determine the quantum state of an individual photon prepared by Alice, there is a case in which he can determine a quantum state by making observations. If Alice prepares many, say 10,000 individual photons, all by the same procedure, so she knows the quantum state is common to all photons, then Bob can design an observation strategy that reveals to him the state Alice prepared. To make the example simple, let's say Bob knows, because Alice informed him truthfully, that the polarization orientation of all the photons is pointing along the same orientation, but is unknown to Bob. To determine this orientation, which specifies the quantum state, Bob can divide his observations into two sets. For the first 5,000 photons, he can rotate his calcite crystal into the V orientation and observe the fraction that passes into the V-pole outcome beam. This tells him the angle the photon's polarization orientation makes with the V direction. But it does not tell him that the angle is positive, clockwise, or negative, counterclockwise, relative to the V direction. To break the time, he can use the second 5,000 photons. He can simply guess that the correct orientation is positive, clockwise, relative to the V direction, then rotate his crystal into that orientation and observe what happens. If his guess is correct, he will see 100% of the photons being detected in the lower beam emerging from that crystal. If his guess is incorrect, he will observe the opposite behavior. In either case, he now knows the correct orientation of the photon's polarization state. This specifies completely the quantum state of the photon's polarization. The take-home message is there is an observation strategy that reveals to Bob the state Alice prepared, but only if Alice prepares many photons identically and passes them to Bob. Measurement schemes such as this are called quantum state tomography, because as in medical imaging, such as computer-aided tomographic CAT scans, the object is hidden from direct view, but its nature can be revealed indirectly by making a series of different measurements. In a CAT scan, X-ray images are collected at many angles, and a set of images is used to reconstruct a view inside the body. Can Bob make copies, clones, of the state of a single photon? In the classical realm of human-scale objects, there is no problem with making copies or replicas of any individual object, an artwork, a page of text, and so on. To do this, we need to examine every aspect or property of the original object. But in the quantum realm, we cannot examine every aspect or property of an individual object because some of them are complementary to each other, as Niels Bohr would say. That is, if you measure a certain property, then there are other properties that you can't measure meaningfully. This defeats the most obvious way of making a perfect copy of a quantum object, including its quantum state. Perhaps we could make a perfect copy of an object, including its quantum state, if we did not try to determine that state, but used some kind of automatic quantum state cloning machine. Perhaps such a machine could work even without determining the state itself. Alas, one can prove from quantum theory that such state cloning or copying is impossible without first destroying the original object. You can't make two from one. The quantum copier machine is permanently out of order. This is an important point, and it plays a role in many applications, such as data encryption, as discussed in chapter 4.
I'm gonna get some water.
This no-cloning principle also reinforces
Oh my
the
God, I'm
conclusion
so weak.
of the previous section, in that the quantum state of a
Okay.
single object cannot be determined by any measurements. To see this, think what would be possible if we could clone the state of a single object. We could make many copies of that object's state, then follow the quantum state tomography procedure described earlier for determining a quantum state, given the availability of many identically prepared objects. This would allow us to determine the state of the single original object in disagreement with what is allowed by quantum physics. What is quantum coherence? Previously, we discussed coherence in the context of classical physics. Coherence in the context of quantum physics, or quantum coherence, is analogous to coherence in classical polarization, except instead of referring to an aspect of the electric field, as in the classical case, quantum coherence refers to an aspect of the quantum state. That is, the two components, A and B, of the quantum state must be stable and not one. Only in this case does Born's rule yield the correct prediction for probabilities. Physicists use the term coherent superposition to describe a combination of two-state components that give rise to a particular quantum state. What are the guiding principles of quantum mechanics? Based on the material covered in the previous section, physicists have drawn some general conclusions about how quantum objects behave when a person attempts to observe or measure them. I present these conclusions as guiding principles of quantum mechanics. These principles largely replace the three aspects of the classical concept of measurement with which this chapter began. Here are the first three quantum principles, based on our earlier discussions. Others are stated in later chapters. Guiding principle number 1. The world is intrinsically probabilistic. Even if you have maximum knowledge about an object, you cannot predict with certainty the outcome of a typical measurement of that object. Comment. Unlike our conception of classical physics, quantum physics makes it clear that the idea of probability is fundamental to understanding and describing nature. This does not mean we need to give up our intuitive ideas of cause and effect. Max Born wrote, "In classical physics, one physical situation depends on the other. This is still true in quantum physics, although the objects of observation for which a dependence is claimed are different. They are the probabilities of elementary events, not those single events themselves." He is saying that one can predict and know probabilities, but not predict with certainty specific outcomes. Guiding principle number 2. The condition of a quantum object can be described by specifying its quantum state, a mathematical representation of everything that is possible to know about a particular quantum object, permitting one to calculate probabilities for observation outcomes in any chosen experimental situation. Comment. The outcomes of observations should not be thought of as measurements of pre-existing properties of the object. Rather, those outcomes provide partial information about the underlying state of the object. If many identically prepared objects are available for study, then by using a clever strategy, you can obtain complete information about the quantum state common to all the objects. But this is not possible if only one such object is available. Comment. If you have access to many objects that are not prepared identically, then the whole collection cannot be characterized by any perfectly known quantum state. In such a state, it suffices to characterize the mixture of states in which the collection of objects is prepared. Such a mixture of states can be characterized experimentally by carrying out a series of measurements using different measurement schemes. Guiding principle number 3. Certain pairs of observed attributes are physically incompatible or complementary to one another, in that they cannot both be observed independently. More generally, the results of measurement depend on the particular measurement scheme with which it is performed. Comment. You cannot answer the question, is a single photon V-pole or H-pole, and independently answer the question, is it D-pole or A-pole? These are incompatible questions. One can say the purpose of measurement is not to determine the values of any pre-existing property, but simply to find out what the outcome will be if you choose to observe a particular aspect in a particular experimental setting. For this reason, observed results are simply called measurement outcomes. This wording does away with any implication that the outcome was predetermined by any pre-existing properties that the object possessed before the measurement. Let's also emphasize that any experimental apparatus used to determine an observed aspect in a particular experimental context will typically change the quantum state of the object. For example, if a dipole photon enters a calcite crystal and exits in the H-pole beam, then its polarization state is now H-pole. This then fixes the probabilities for any further observations of polarization. What does quantum mechanics really describe? I will answer this question with a quote from Max Born. Thinking in terms of quantum theory needs some effort and considerable practice. The clue is that quantum mechanics does not describe a situation in an objective, external world, but a definite experimental arrangement for observing a section of the external world. He goes on to say, our sense impressions are indications or signals from an external world which exists independently of us. Chapter 3. Application. Quantum data encryption. Can quantum physics be harnessed to create perfectly secure internet communication? Yes. In recent decades, scientists have learned how to use the quantum nature of light to make messages and other data almost perfectly secure. Quantum physics allows us to encrypt messages in ways that cannot be cracked by any computing method in a reasonable amount of time. Data encryption using quantum techniques is an excellent topic for our first foray into technological applications of quantum physics. How does encryption keep messages secret? For financial, industrial, military, or personal reasons, people often want to send messages so that only the sender and intended recipient can know its contents. Typically, encryption systems use some kind of replacement system, in which letters or numbers are replaced by other letters, numbers, or symbols, according to some preset but secret rule. The more complex the rule, the harder the system is to crack. The art of sending messages in